Basic Mechanical Drives, Part 1, written and presented by me, Jean Legouis. Here's legal stuff. Enjoy. Right, so, purpose of this set of lectures is to provide an overview of the general types of drives used in industry. First type we'll be looking at is direct drives. It's not a good idea to rigidly connect together what's supposed to be coaxial lined up shafts. Any misalignment will cause bending stresses and vibration. Misalignments are inevitable due to small differences in tolerance and load-induced or thermally induced movement due to support due to the weight or bending under load. Misalignment is allowed for by connecting the shafts using a shaft coupling. Each coupling is connected rigidly to one of the two shafts by a key or some sort of contacting friction bush or by some other means. The motor and drive assembly is then adjusted to minimize the initial misalignment. Then tightened down, and the half couplings are finally connected together by the flexible element. Choice of couplings depends on things like the speed and energy level of the connected machines, the degree of misalignment which the coupling can tolerate, the torsional vibration level. For instance, a flexible spider coupling might be expected to cater for greater misalignment than a gear coupling, and also to provide more damping. But the torque capacity of the gear coupling will be much greater than the flexible spider because the metal gear teeth are much stronger than the rubber spider. Here are some of the less common couplings that you may encounter. Now, according to Wikipedia, the advantage of direct coupling is that it increases efficiency. We've not got wasted energy due to friction from belts, chains and gearboxes. It reduces noise, being a simpler device, has a longer lifetime, there's fewer moving parts, less prone to failure, once again fewer moving parts. It can deliver high torque at low RPM. It's a stiffer system, so hysteresis, backlash are all minimized. The main disadvantage of the system is you generally need special motors. Remembering that an electric motor will try and start at its running speed. So basically it'll go from 0 to 1500 or 3000 RPM in as quick as possible, a few tenths of a second. The beam coupling consists of a single or multiple helical cuts in a cylinder of metal. This typically accommodates parallel misalignments of about 0.5 millimeter and angular misalignments of about 7 degrees. They're primarily used for motion control applications where torques are typically below 10 Newton meters. Zero backlash designs are also available. There's two types of bellow coupling. The small bellow coupling are also motion control applications. The large rubber bellow, sometimes called a flange coupling, are typically used for pumps and provide high torque transfer while dealing with large misalignments, axial, parallel and angular. Vibrational and torsional oscillation is damped by the rubber. Chain couplings are suited to power transmission applications and are used to transmit power up to and into the hundreds of Newton meter range. Angular and parallel misalignment allowances are typically 2 degrees, about 0.5 millimeter, respectively. Typical chain couplings use special chain sprockets and double wide roller chains whose clearances permit the design to operate as a flexible coupling. Curved and straight jaw couplings are used for both motion control and light power transmission applications and consist of pairs of multi-jawed hubs that mate with elastomic spiders. The design allows for backlash-free torque transmission. Accommodation for parallel misalignment usually approaches 1/4 of a millimeter and angular misalignment about 1 degree. Elastomeric spiders give these couplings some damping capacity. These couplings often operate without lubricant and can transmit torques up into the 100 Newton-meter range. They feature ease of installation due to the simple construction. Low cost. The star rubber element is the only spare to be replaced in maintenance. They're available with spacer arrangement for distant shaft connections. They have high vibration and shock load absorbing capacity. The performance is unaffected by moisture, grease, oil, or temperatures up to 100 degrees Celsius. Gear couplings transmit high torques. They have misalignment capacities generally about 1/2 a millimeter in parallel and 2 degrees in angular. Gear couplings are often used in pairs with spacer shafts to span the distance between driving and driven equipment. They sustain very high torque ratings. They're suitable for high-speed applications. The heavy-duty design is still flexible. It counters all types of misalignment, axial, parallel and angular, and large axial movement capacity. They're suitable for high-temperature environment up to 120 degrees Celsius. Specially designed crown teeth can reduce backlash and radial clearance. Grid couplings employ spring-like connecting elements that weave between slots machined in the coupling hubs. They are capable of high torque transmission with the added bonus of shock absorption and torsional vibration dampening. They operate without lubricant. They are appropriate for power transmission and capable of handling parallel misalignments up to 7.5 millimeters and angular misalignment of about 1/4 of a degree. They combine high power rating and high flexibility, like elastomers. Because it's 100% metallic parts, make it suitable for high ambient temperatures. The robust construction has no fast wearing components. The flexible grid spring are quickly replaced without disturbing connecting equipment. It protects against shaft misalignment. It sustains and reduces the vibration while transmitting the power. The Schmidt coupling are designed specifically to operate on shafts that are offset. They aren't flexible coupling in the strictest sense, which are designed to accommodate slight misalignment in shafts that are theoretically parallel and square to one another. Schmidt couplings are used in papermaking, printing and similar machines and function more like a one-to-one gearbox in a more compact space. They were designed in 1960 by Richard Schmidt, who was working for NASA, and he was asked to develop a system for a rocket propulsion system for a zero-gravity environment. A universal joint, or UJ, or U-joint, or Cardan joint, Spicer or Hardy Spicer joint, or Hooks point joint. It's a joint or coupling in a rigid rod whose axes are inclined to each other. Is commonly used in shafts that transmit rotary motion. It consists of a pair of hinges located close together, orientated at 90 degrees to each other, connected by a cross shaft. The universal joint is not a constant velocity joint, but tends to pulse twice a revolution. This pulsing of the torque increases as the misalignment of the shafts increases. And that's the end of part 1.